Okay, this is a very important section, and this is on model evaluation techniques. So we can try lots of different models, lots of different algorithms. We can use neural networks, we can use regression, we can use trees, we can use lots of different methods, but we want to know, how good these methods are. We want to be able to compare the results and talk about how good the results are. And so that's what we mean by model evaluation techniques. And we're going to talk specifically about these measures here. The most basic one is called accuracy. And then we're going to talk about some other things: true positive rate, false positive rate, true negative rate, false negative rate, and precision. Um, so now, um, when we do when we run a model, we get we can get what's called a confusion matrix. Um, let's see. In this example, you can see this table 6.1. We had a model which is like a medical test, which is supposed to predict whether someone is sick or healthy. Maybe it tests for the presence of a certain disease or not. Okay, so you can think of that as like a model, just like a neural network. It's not a neural network because it's a physical test. Like you take somebody's blood and then you check to see whether they have a disease or not. Let's say it's malaria or something like that. So um, it's a physical test in that case. But you can think of a neural network sort of works in the same way. You'll see what I mean in a minute. So for example, because the point is that when you get this test to see if you have malaria, the test is not foolproof. It's not always right. Even though it says that you don't have the disease, it doesn't necessarily mean that you really don't have the disease. Even though it says that you do have the disease, it doesn't mean that you actually do have the disease. The test could be wrong. Okay, so we're talking about that kind of scenario. Okay, now, so what we have here is what we call the predicted and the actual. Okay, so the predicted is what the test predicts, and the actual is what's actually true. So like we said, what the test predicts and what's actually true are not necessarily the same. You may be sick, but the test doesn't say that you're sick. Okay, so what we have here across the first row is that since we're going across the row, we're talking about actual. So the people are actually healthy. Now usually, when you're talking about medical tests, that means you tested negative. Okay, you tested negative for the disease. That's called healthy. Okay, so the people were actually healthy. Now, this will be a number, this will be a number, this will be a number, and this will be a number. So suppose this number is 10. So what that means is that among the people who were actually healthy, the test predicted that among those 10 it predicted healthy. Okay, and suppose this is 20. So what would that mean? That 20 would mean that among the people that were actually healthy, the test predicted wrong, predicted incorrectly, that 20 of them were sick. Okay, so that's what this number means. So it might look like this. Okay, so you have what the test predicts and the actual. So, for example, here's 10. This means that if you read it across the row, actually the person was healthy, but there were 10 people that were actually healthy, but the test predicts them as healthy. On the other hand, there were 20 people that the test predicted as that they were actually healthy, that the test predicted them as sick. Okay? And here, what's this 15 mean? That means there were 15 people that were what? Actually sick, but the test predicts them as healthy. Okay? And here, there were 80 people that were actually sick and the test predicts them as sick. Okay, so we can ask which one, where are the errors and which ones are correct? So here, these are correct, right? They were actually healthy and the test predicts them as healthy. And here also, they were actually sick and the test predicts them as sick. On the other hand, here, they were actually sick, but the test predicts them as healthy. And here they were actually healthy, but the test predicts them as sick. So this one and this one are errors. So there were how many errors? There were 35 errors out of how many altogether? That's, what is that? 115, is that right? Yeah, 115. Okay, so 30 out of 115 were wrong, and the rest were correct. Okay, now this is the same, you could do the same thing like with a neural network. You might be trying to, you have the actual state of things, like you're trying to predict when there's a gust, and this might be gust and no, or this might be 0 and this might be 1, so this might be no gust and gust. And there was, so you might predict in 10 cases, what did we say, this was no gust, you predicted there was no gust. And I'm sorry, you predicted there was no gust and there actually was no gust. Whereas in 20 cases, you predicted there was no gust and there actually was a gust. So that kind of thing. So it's the same kind of scenario. You have a test and you're trying to determine whether it is, how accurate it is. Okay, now in this, test, we only have two categories, healthy or sick, or 0 and 1. But we could have many different categories, and so this table could be bigger. So you could have many categories along here, and then the same number of categories down here, and you would have a similar kind of reading from that. All right, let's go back. So here, instead of actual numbers, we just have A, B, C, and D. So again, which ones are the correct predictions? A and D are correct, and B and C are not correct. Okay, now what did we say before in terms of the accuracy? We said, how many were accurate? This one and this one, that's 90. Did I say, I don't know what I said before. 90 out of out of a total of 115, right? So that's called the accuracy. That's the percent right. And then we can also talk about the error rate, and that's going to be what? 20 plus 15, 35 out of 115. So that's going to be the error rate. So we have, so what is the accuracy? In here, it's A plus D over A plus B plus C plus D. The accuracy is A plus D over A plus B plus C plus D. And what's the error rate? It's B plus C over A plus B plus C plus D. Do they have that here? No, they don't have that. But you could, WECA, I think, gives you that also. I'm not sure, actually. Okay, so that's one measure of how well the test did. However, going back to the example when you're talking about healthy and sick, okay, so let's say that this is a test for cancer, okay, it's breast cancer, some kind of cancer. So here we have what, 10 people. The test said they were healthy and they were actually healthy. Here we have 20 people. The test said that they are sick, but they're actually healthy. Here we have something. Here, what do we have? Here we have the test predicted them as healthy, but they're actually sick. Okay, so which one of these four blocks is the most sort of consequential? Or I should say, or maybe I should ask, which of the errors here, and there was actually only two errors here, this one and this one, which one is more consequential? Which one is more important? which one is more important? All right, well, I think it's clear that this one is sort of the most important error, because here we have the test is saying they're healthy, but they're actually sick. So for these 15 people, they have a kind of a problem, right? Because they're going to go home and think they don't have any cancer, and then they're going to get sick and die, right? Now this is also an error, but it's not really as important in some sense as this one was. Why? Because the test tells them that they're sick when they actually aren't. Okay, so that's not so good, because that means they're going to have to go in and get more tests and get checked out more and so on, and that's not so great, right? It's going to scare them, it's going to cause them trouble and so on, but it's not as severe as this error in terms of the consequences of the error. So we want to distinguish between these different kinds of errors. So this one, remember, this was called, what was it called again? Was called negative, and this one was called positive. So this one is negative and positive, negative and positive, right? That's the way we named them. So we have this error and this error. This is called is this called a false positive or a false negative? So we're talking about what the test reports, right? So the test reports this as positive, but it was wrong. So this is called a false positive, right? And this one, what is this called? This is called a false positive or a false negative. So here, the test reports negative, but it's not true, so it's a false negative. So this is called a false negative, and this is called a false positive. And in this case, the false negative is much more important. The number of false negatives, or the amount of false negatives that the test is reporting, or the percent, is important. Okay? So over here, that is C is the false negative, right? And B is the false positive. Okay, now what we do is we define something. We just said we define the accuracy. We also define what's called the true positive rate and the false positive rate, and then some other things. So here's the false positive rate. What did we say was the false positive again? Here, I think, right? These are predicted as positive, but they're not. That's not so important, but that wasn't the important one. C was the important one. But so this is false positive. Now what's the false positive rate? It's this divided by something. And what is it divided by? It's divided by A plus B. So it's this divided by these two. So what can we say it is? It's from out of all the healthy people, these are all the healthy people, A plus B, the ones that are predicted as sick, okay, the ones that are falsely predicted as sick because they're actually healthy. So from out of all the healthy, the ones that are sick, the percentage that are predicted, as sick, right? So that's B over A plus B, right? B over A plus B. That's called the false positive rate. And what is the false negative rate? Remember, that one was sort of more consequential. That was here. C, we said, was more consequential. And it's C over C plus D is the false negative rate. C plus D. So it's this over this plus this. Okay? So what is that? So that's the percentage of people that are predicted as healthy from the group of all sick people. So what percent of all the sick people are predicted as healthy? Okay, that's called the false negative rate, right? Okay. Now, Weka gives us all of these values. It tells us, it prints them out. Now, you don't need it you don't need Weka to do it because you can just use these formulas very simply because Weka also gives you the confusion matrix. But Weka does print out the false positive and false negative rates for all of these. Okay, and it also gives the true negative rate, which is this, and the true positive rate, which is this. Okay, so all of these can be relevant depending on what the test is about. And then there's some other ones that are used in data mining. This is another test. This is another test. This is another test. So this one is what? Oh, by the way, there's some. Oh, we skipped one. The precision of the test. The precision of the test. What's that? By the way, some of these have other names. Like there's a sensitivity is one of these. I forget. That's used more in the medical profession. But sensitivity is one of them. Anyway, we'll worry about that later. There's one more here, precision. What's that? That's also used frequently. So that's D over B plus D. Where's that? D over this one plus this one, these two. So what's that? That is from the people that are actually, no, sorry, from the people that are predicted as sick. So our test predicts them as sick. How many are actually sick? That's called the precision. Okay. Now there are, maybe we'll talk more and try and make this sort of clearer by saying what's important when and so on. But right now let's just stick with the definitions. Okay. So we have all of these definitions. These are measures of the different kinds of accuracy of a test. Now, we're talking about a test here, like I said before, that has just two possible values. Okay? So the predicted outcomes can be either only healthy or sick. And I said before that you can have more than just two outcomes, and you can do the same kind of thing. However, sometimes we're trying to predict something which isn't categorical like this is. This is categorical, has just two values, two possible values. For example, we might be trying to predict the temperature, right? Given certain kinds of weather conditions, what's the temperature going to be? Or something like that, right? So we're trying to predict the temperature. It's not just, there aren't just two values for temperature usually, right? You know, there's an infinite number of values that temperature can be, anywhere from whatever, 0 to 100, but an infinite number of values in between 0 and 100, for example. So that's not a categorical variable, and in that case, you know, looking at this kind of table doesn't make any sense. So in that case, we don't have these kinds of measures anymore. Okay, so like when you did regression, we had an entirely different way of measuring accuracy and error, and that was called R squared. And that was a percent number, but it was nothing like this. Okay, so if you're, if it's not categorical, you don't have anything like this. You don't have any, what we call a confusion matrix. Okay, but if it is categorical, you do. And in one of the assignments, I ask you to convert the GUS data to categorical variables. Then you can definitely do this kind of evaluation of the accuracy of your model. Okay, let's read through just a little of this. In figure, I'm sorry, if we revisit figure 1.2, we would see the term evaluation in the data mining lifecycle. So what that means is, you know, when you're doing data mining, what you'll do is you'll build a model and then you'll test it and see how good it is, and you'll use these evaluation techniques that we just talked about to test it. And then after you test it, then you might go back and, you know, tune your model a little bit differently to see if you can't make it perform better. So that's kind of a cycle, right? You build the model, you test it, then you go back and tweak it or tune it up, and then test it again and repeat that over and over again. Now, I'm not going to ask you to do that in general, but if you were in the real world, you'd be doing something like that. If you had something where you're trying to predict something about your customers, like when customers are going to leave your company, you test the model, and then it didn't work so well, then you try and tweak it a little bit, make it work better, right? And you'd keep fine-tuning it as much as you could. This is one of the important aspects of data mining, of the data mining task. We can grasp the concept of this task from a simple example. When we go to the supermarket to buy grapes, we first check the quality of the grapes before we decide to buy them. How do we check the quality? Well, if they're crisp, stain-free, and sweet, we go for it. We have some preconditions, for example, seedless grapes. We may have some preconditions, for example, seedless grapes, which will narrow our search among the grape varieties available. In some ways, we follow the same procedure to choose a data mining model. We choose some performance criteria which are reliable and valid. So we might choose accuracy. Reliability indicates that the performance criteria should work most of the time, if not every time. We wouldn't want to work with criteria that may fail us on many equations. Validity indicates that the performance criteria are relevant to our objectives. If our objective is to pick nice grapes, the criteria we choose, for instance, crispness, no stains, and sweetness, should be appropriate to distinguish grapes which are nice from those which are not nice. So this is our test, and hopefully our test, we can see whether they're crisp, whether they don't have stains, whether they have sweetness or not. But hopefully these actually relate to whether we're going to like them or not. So we might predict that they're crisp, and maybe the grapes are actually crisp, but that doesn't, and then find out that crispness has nothing to do with what we like. So that wouldn't be so great. So validity indicates that the performance criteria, in this case crispness, for example, are relevant to our objectives. Our objectives are like getting good grapes. Just because they're crisp, maybe that doesn't really mean that they're good. Okay, so that's the concept of validity. Okay, the process of model performance checking against certain criteria is called evaluation. So we looked at evaluation concepts just before. Model evaluation is a very important task in data mining, because model deployment involves capital expenditure. Model deployment means using the model and developing the model. So if you're a big company and you're building a model to predict whether somebody's going to purchase a product or not, it costs a lot of money, could cost a lot of money to build that model and then to test it. So you want to evaluate the model before building it, or before deploying it rather. So it requires capital expenditure and investment. And if a model is invalid, an organization's time and money are wasted. Comprehensive model evaluation involves application of statistical, heuristic, experimental, and human analyses. So these are sort of different approaches to different parts of evaluating a model. However, in this chapter we will restrict ourselves to statistics only, and each criteria is analyzed in the context of classification strategy. Alright, we'll continue with this later, or with the second video. Let's stop here.